the Global Andrology Forum, which is the host of today's webinar on medical statistics for online research. I want to welcome all of you to this webinar, which is planned today for 2 hours. And we have a galaxy of very, very highly renowned speakers. The first part will be an introduction or welcome from Dr. Rupin Shah, our senior advisor in Global Andrology Forum, followed by the program chairman, Dr. Nicolas Garrido from Spain, who will be speaking on the introduction to biomedical statistics, followed by Professor Ralph Henkel from UK, who will cover the data description. Session 3 by Professor Wael Zodi will talk about comparing means between groups. Session 4, comparing proportion between groups by Dr. Ahmed Haraz. Then I will give you a brief description or introduction of our organization, Global Andrology Forum, followed by Dr. Nicolas Garrido, who will take some questions. So this webinar is on medical statistics for online research, a customized course for clinicians and non-clinicians. Now, many of you will wonder why we are doing such a course. What is the need for such a course? Well, let me tell you something. Basic statistics is really important for clinicians and researchers, because it allows them to critically evaluate the results of medical research. In particular, need to be able to understand the meaning of statistical terms such as p-value, the confidence interval, odds ratio, because these terms are used to describe the results of clinical trials and other research studies. And it is important for clinicians to be able to interpret them correctly in order to make informed decisions about the patient care. Furthermore, clinicians need to be able to understand the limitations of statistical analysis. No study is perfect, and there is always the possibility of bias or error. And the clinician need to be able to, they should be aware of these limitations to put the results of research studies in a proper context. Finally, clinicians should be able to communicate the statistical information to the patients in a clear and understandable manner. Patients often want to know about the risk and benefit of different treatment options, and it is important for clinicians to be able to explain this information in a way that the patients can understand. So it is really a very critical webinar that we are offering for the very first time. Such type of program have never been offered in any part of the world. So I must tell you that this program took a great deal of planning, brainstorming, thinking, talking to our stakeholders, and then we came out with these ideas with the help of our statisticians who are working alongside us in the Global Andrology Forum. I will come back again at the end, but right now, without taking further time, I ask project coordinator, Ms. Liliana Ramirez. She is our Chief Research Coordinator for the Global Andrology Forum, along with our backup support from Dr. Missy Savira, to start the program. The program is essentially everything is being recorded by our speakers to make sure that we can start and finish the program on time. But all the speakers, except for maybe Professor Ralph Henkel, are available, and they will come back towards the end. So they are all physically available and attend. Thank you very much. And I ask Ms. Liliana to take over. Thank you.
Good day, morning, afternoon, night, wherever you may be. And welcome to this special GAF webinar on medical statistics, which is actually a very, very important subject for clinicians and researchers. One of the major activities of GAF has been to train clinicians and researchers in performing good systematic reviews and meta-analysis. And part of a standard training which Dr. Arafa has now formalized, includes extensive exercises on how to do a scan, search for abstracts, identify duplicates, verify the validity of an abstract, get the full paper, select the appropriate papers, and then how to do data extraction onto an Excel file in a manner that the data is then amenable for a good statistical analysis. And that is where the clinician researcher starts fumbling, because most of us know very little about medical statistics. And today we hope to fill that gap. Fortunately, GAF has 4 very senior statisticians who have been helping us with our numerous publications. And today they are going to give a series of talks illustrating all the basic and important concepts that we need to understand in medical statistics. Now, honestly, 2 hours is not enough. And I'm sure most of you will get a glimpse of what is required, but will still have much confusion. And therefore, we will be posting the recording right away. And I hope that you will go back to the recording and listen again to clarify areas that are unclear, and then additionally go on the net and search for specific topics where you feel you need more education. If you can use this meeting as a kind of motivating stepping stone into the world of medical statistics, then it's very possible that in the next 1 week you will become fairly clear and competent and knowledgeable about at least how to use them, even if you cannot still perform them independently. Then, of course, we will come back to further and advanced training in future. I wish all of you a wonderful 2 hours learning something that is very important and very useful. And thank you for joining us.
Hello, everybody. I am Nicolás Garrido, Director of EB Foundation in Valencia, Spain, and it's a great pleasure for me being with you today for the Medical Statistics for Online Research course in Session 1, Introduction to Biomedical Statistics. The learning objectives are first to describe the various techniques for statistical analysis, introduce the different research designs that address diverse research questions, and how to draw conclusions and correct interpretations from research data, and also deliver the appropriate message which can be properly incorporated into biomedical knowledge and clinical practice. We will talk and cover about the utility of statistical analysis for biomedical research, how to calculate the number of cases needed in each research project, what does a p-value mean, the difference between clinical and statistical significance, and how to extract take-home messages from the results of statistical analysis. Biomedical research means answering clinically relevant questions. To this end, epidemiological studies or medical research studies are the set of intellectual and experimental activities carried out systematically aiming to generate knowledge on the causes that originate human disease or the effects of certain interventions on them. Then we want to establish the relationship between the causes of the disease or interventions on them acting as independent variables, on the influence they have on the emergence or resolution of the disease, which may act as a dependent variable. Then the systematic search for answers to relevant and structured clinical questions by means of scientific methods is what we name biomedical research. There are different types of research questions that can be addressed. For instance, trying to define the characteristics of a disease that are present in sick and differ from healthy patients, which are the best diagnostic tests discriminating both sick from healthy patients, to define the patterns of disease occurrence, the frequency populations, which are the etiological factors and determinants of the disease, to define prevention strategies, how influent the different factors on the natural course of the disease, but mainly which is the best treatment for a given disease. And this is also based on the concept of evidence-based medicine, which is an approach to medical practice intended to optimize the decision-making by emphasizing the use of evidence from well-designed and well-conducted research. In this sense, we need to keep in mind that health interventions should be tested before being introduced into clinical practice to find out whether they work and whether they are harmful. However, research studies will only provide with reliable answers to these questions only if they are appropriately designed and analyzed. And these are not trivial tasks. There are many different methodological challenges arising when evaluating fertility interventions, including flexibility in outcomes and analysis, the use of surrogate outcomes instead of using live birth, the use of inappropriate denominators, evaluating cumulative outcomes and time to live birth inappropriately, and allowing each patient or couple to contribute to a research more than once. How does biomedical research work? What do we mean with the scientific method? The scientific method is structured as follows. We can define a problem or an area of interest to be researched. We need to look for already existing sources of information. If not answered yet, we can formulate a hypothesis that frequently means the correlation between two different variables. Then we will design and conduct a study that will allow us to get information, draw conclusions, and then report results and modify or adapt our clinical behavior based on the knowledge that we obtain. So what are statistics and statistical analysis for? Statistics in biomedicine means all the techniques to study a certain population from the collection of information, data analysis, and the interpretation of results by generation of models, inferences, and predictions associated with the phenomenon in question, but also, and most importantly, considering the randomness of the observation. It's used to model patterns and draw inferences about the population under study. The aim is to get useful conclusions to be able to make deductions about the totality of the observation made based on numerical information. The statistical techniques will allow us to discriminate when we find differences between two means or proportions, for instance, if these differences that we observe are caused by chance or not with a high probability. With this, we will accept or refute the working hypothesis based also on the experimental design of the study. In other words, these are a number of tools that allow us to estimate how well your findings can be extrapolated to the general populations and how strong conclusions can be stated from them. A measure of how sure can you be that our results actually represent the truth in the overall population. Let's see some general concepts on the research methodology. There are different kinds of studies. For instance, depending on the type of results that we obtain in the study, we can have descriptive studies, including a type of methodology in order to deduce a circumstance that's being presented and applied by describing all dimensions. The classical descriptive studies include the case series studies and the prevalence studies. The function is just to describe how something is happening in a population. On the other hand, we can define an analytical or etiological study as an epidemiological study in which association or causality relationships between variables are established during the analysis of the study. Then, when an analytical study is proposed, it's known a lot about the disease and probably coming from a previous descriptive study, and is the most common kind of research that is conducted in medicine. These typical analytical studies may include the study of cohorts, case and control studies, and randomized control trials. And so analytical studies allow establishing the relationship between the causes of the disease or interventions on them, acting as independent variables, and their influence on the emergence or resolution of the disease, which act as a dependent variable. Depending on several aspects of the studies, we can find different ways of classifying them. Basically, the parameters include the moments of data collection, the way we select patients, the actions we conduct on patients or their data, and the temporality during the study. According to the moment of data collection, we can have prospective studies when the data collection is programmed in the future from the moment on planning the study. And we can find also retrospective studies. These are studies looking for past information. So the study starts after the studied variables have already occurred and been retrieved. Depending on the existence of follow-up, we can have follow-up studies, including monitoring, and also transversal studies, when the exposure and the effect are measured at the same time. We may find observational studies where the researcher does not interfere, just observes and describes reality, as an example of the case and control studies and studies of cohort and prevalence. But we also can find interventional studies where the researcher introduces the variables in the study, interfering in the reality and the development or evolution of the disease. Depending on whether there's randomization or not, we can divide it into quasi-experimental studies and the most probably well-known experimental studies, where patients have been included randomly and in a prospective way in order to evaluate how an intervention changes biomedical related outcome. It's a case-controlled study when subjects are selected according to the presence, in the case of the cases, or absence in the controls of a defined disease. Once the individuals of each group have been selected, the research is intended to elucidate whether they were exposed or not to some characteristics of interest. In the case of the cohort studies, the patients that comprise the groups are selected according to the presence of a determined characteristic or exposure, and we will observe on them the frequency with which the disease appears within each group. It's also follow-up projected on incidence study, and it's intended to measure the causality between the risk factors and the disease. Then, clinical trials include those experimental evaluation of a product, substance, drug, diagnostic, or therapeutic technique in order to evaluate efficacy and safety of its application. It should be only conducted when there are reasons to believe that the treatment could be beneficial for the patient, and this is assumed to be the highest level of evidence in biomedical research. It consists in an experimental and prospective study in which the researcher triggers and controls the variables and the subjects that are assigned randomly to the different interventions that are compared, presents the lower systematic errors or biases, and therefore comprises the best scientific test in order to support the efficacy of therapeutic intervention. It's essential the existence of a comparison group, the control group, that enables to test whether the new intervention is better or worse than the pre-existing treatments. Not everything should be demonstrated by a randomized control trial, and in this slide you can find some nice examples, some fun examples. It's important to have a reasonable doubt, and also that the potential benefit justifies the risk. A clinical trial shows the highest level of evidence because the randomization will take care of the known and unknown statistical variables that can be present, disturbing the relationship we are interested in describing. Then this introduces a control factor to avoid biases. This, in addition with meta-analysis, is the base of what is known the evidence-based medicine approach. population versus sample, sampling errors, uncertainty, and biases. We would like to know what happened in the entire population just by studying a sample. In our research projects, we will probably get a sample to study, but we want to infer what we learn in our sample to the overall population. That's what statistics help us to do. Descriptive statistics versus inferential statistics. We mean inferential or inductive statistics when we use the results of the descriptive statistics relying on the calculation of probabilities to obtain conclusions about a population from the results obtained in our sample in order to test any hypothesis. Because the end goal of a research project is to contrast hypotheses, is frequently to establish a relationship between two variables. These relationships is aimed to be established at the level of the entire population, but we will never be able to study them all. We only study a sample, and from our study of the sample, we would like to draw conclusions on the entire population. Then, all the relationships we want to establish between variables look approximately the same. We may have exposure variables, which we name as independent variables or intervention or risk factors. We would like to relate them with outcome variables, which are named dependent variables. And we would like to answer these questions. Okay, is there any relationship between them? As one changes, does the other change? Is this change due to chance or not? So can we believe this will be in the entire population or not? But moreover, we would like to know also, are there any other variables that could interfere with the relationship we want to study? Are there any confounders or effect modifiers? Can we control them through the design or the analytical, the statistical tests that we can perform? So it's very important in our field to choose the most adequate outcomes. IVF is a very complex thing to analyze. We have many different ways to measure IVF or reproductive success. We don't have standard units. The main result may differ depending on the study, and the cure of infertility may include several different outcomes. Also, the definition of assisted reproduction treatments, it's very blurred. It ends after a single embryo transfer, after all the embryos have been transferred from a single ovarian stimulation. Do we need for multiple attempts? It's extremely complex, and we should also approach any research project depending on which is the exposure variable and the outcome that we would like to measure. And depending on the case, we need always to apply an intention to treat approach. We need to be careful with measuring as failures, cancer cycles, no transfers, block embryos. So depending on the design, they should be accounted as failed attempts. So depending on which is the step, the approach is different. What about the sample size and the statistical power? Sample size calculation is the choice of the number of observation or replicates that we need to include in a statistical sample for a study. Sample size is an important feature of any empirical study in which the objective is to make inferences about a population from a sample. So the sample size for a study depends on the basis of the cost of obtaining data and the need for sufficient statistical power. So what is the sample size calculation based on? First, we need to know which is the minimum effect size we want to study. And this is based on the decision from the investigation of what's clinically relevant, but also based on the previous data available on the measurement and the variability of the main outcome. So calculation of the sample size will depend also on practical aspects, such as resources available, recruiting time, and then we can calculate and recalculate until we feel all these different areas are covered. For instance, imagine a randomized control trial checking two different embryos transfer catheters. Which is the clinically significant or relevant different from a researcher? Is adding 10%, 20%, 30%, 40%? This will depend on the opinion and judgment of the investigator about what is clinically sound. Imagine that the baseline is 35% success rate and the standard deviation is ±5. So based on previous data or other published literature, we establish the threshold and then we can calculate which are the number of cases needed to reach an improvement, let's say by 10, by 12%, something like that. So the sample size will depend on which is the difference you want to be able to check and which is the baseline result. Here you may find an example. For changing a success rate from 35% to 47%, you may need, in order to get an alpha error of 0.05 and a beta error of 0.80, a number of cases of 207. This is an example of a practical case of publication of calculation of the sample size. Interestingly, the bigger is the difference you want to be able to demonstrate, the lower the number of cases necessary. In this example, you may find that 50% differences in pregnancy rates may be needing only from 11 to 15 cases per arm. In a retrospective study, you cannot calculate the number of cases needed. You just need to check the power or sensitivity of the test, because the cases included have been already defined because are those cases that you have available. It's important to remark that the databases need to have the proper structure, since the statistical software have no brains, and the data should be assessed for credibility, the database clean, well-structured in rows, columns, and all data clean, the measurements and categories before you can enter them into any software to test. What statistical tests should be used? They will depend on the number of cases and data distribution, the number of groups to compare, if they are independent on related samples. But basically, depending on the exposure and result variables, and depending if they are categorical or quantitative, you can use all these different statistical tests and approaches that we will be covering in subsequent sessions during this course. Most importantly, how to read the information, how to interpret the p-value. The relationship that we are studying is confirmed, and it's highly unlikely to be the cause of the random sampling error, which means that it's very credible. This is a significant p-value correct interpretation. If we repeat the same experiment 100 times, at least 95 of them, the observed relationship would be confirmed with that effect or greater. Even so, that the change in exposure variable is causing a change in the result depends also in the control of other variables, on the study design, the sampling, etc. How should a not significant p-value be interpreted? The relationships we are studying with the data we have, we cannot rule out that it is due to random sampling error, which means that we cannot trust it to be true. Depending on the number of case studies, if they are few, the power is low. And even so, the change in these variables will depend also in the design, sampling, etc. What do we mean with statistical significance? This only implies that the differences found in the sample are very unlikely to be due to chance. It's extrapolated to the population, not due to sampling error. The larger the sample size, the more likely is to achieve statistical significance. But is the difference found credible? This is the question helping to be answered. But concerning clinical significance, in addition to being statistically confirmed, the confirmed difference is clinically relevant. It is a subjective assessment of the researcher. It is answering the question, is the difference found important? What does statistical significance and clinical significance mean? As we said in previous slides, and you can see in these examples, if you have a case with a lot of sample size, a huge sample size and a very low p-value, this means it's statistically significant, also clinically may be irrelevant. And on the other way around, with a small number of case studies and a non-significant p-value, you still cannot discard that this is by chance, but the clinical relevance of the difference should be probably more studied in detail. So how to correctly interpret statistical analysis results? Is the evidence important statistically, clinically? Cost and benefit ratio acceptable? Which is the effect size? Which is the main outcome considered? Which is the evidence level and quality? How much evidence is enough evidence? We need to take decision. There's a lot of things to be taken into account. One of the objectives of the investigation is to establish causal relationship. This is not given by a statistical test alone. It can be only done if we have done a study with the adequate design, mainly experimental, where all the confounding factors are to some extent controlled. So finally, I would like to stress how to interpret the literature. Also, for translating our results to clinical practice, the extended PICO-SHIELD. We want absolute answers, but we frequently can get only probabilities. So for each paper you read, for each paper you write, you need to focus on patients, interventions, controls, and outcomes within the context of the p-value, the effect size, the design, the control of potential biases, and the possibility to generalize your results. And to end my talk, I would like to go with an example, the MOXIE trial. What does really mean? This study concluded that antioxidants do not improve 7 parameters or DNA integrity among men with male factor infertility. But I strongly disagree, because you cannot generalize this conclusion, because it should be established only in the kind of patients they introduced in the study, the kind of intervention, and not all the antioxidants available out there, and the kind of outcomes that these researchers studied in their work. Because at the end, statistics are numbers that tell a story, and we should be able to read them properly and learn from that. I hope you enjoy these next sessions, more focused on specific practical aspects of the statistical analysis, and we will be glad to answer any questions may come from your side. Thank you so much for your attention. Hello, everybody.
Hello, everybody. My name is Ralf Henkel, and I'm presenting my presentation here on data description, which is an important part of statistics. This is the outline and description of my presentation. We are talking about variables, description and its representation, principal statistical distribution of normal or not normal, as well as mean, median, standard deviation, standard errors of a mean confidence interval, and odds ratio and risk ratio. In general, one can define variables as a characteristic that can be measured and that can assume different values. For instance, height, age, income, or whatever. But there's other different aspects that we have to consider as well. And basically, we can distinguish between two main categories of variables. which is quantitative or numerical, which can be expressed in numbers, or categorical, which is just a quality, so it's qualitative. And this slide actually shows this a bit in a graphical way. We have a variable which we distinguish between quantitative, which can be described in numbers, for instance, sperm count, motility, and so on. On the other hand, we have categorical variables where it's just different categories, sick or healthy, high, medium, low, and so on. If we go back to the quantitative variable, there's continuous variables, that is just numbers that can, like for hormone concentrations, that can take definite numbers for the decimal point, or discrete numbers, where it's only certain numbers, discrete numbers, 1, 2, 3, 4, like the number of children. On the other hand, these categorical variables, there we have distinguished ordinal variable, that is, for instance, the grade of a varicocele, 0, 1, 2, 3, or a nominal variable, that is when male, female, a yes or no, you have a varicocele, yes or no, and such things like this. So going into these variables and definition of a variable for the quantitative or numerical variables, it is a quantitative variable is a quantifiable characteristic. Those variables are numbers that can be either continuous, like I said, the hormones, or here, for instance, also sperm count, motility, ORP, or testosterone concentrations. Or on the other hand, it can be a discrete variable, which can only assume finite numbers of real value. It's 1, 2, 3, 4, and so on. Or for instance, for grade of varicocele, 0, 1, 2, 3. On the other hand, the categorical or qualitative variables, which just describe a quality of that parameter, that is defined as a variable that refers to a characteristic that cannot be quantified. So they we distinguish between ordinal variables, it can be good, better, excellent, or nominal variables, where we see that is one that describes a name, like a male or female, pregnant, yes or no. So we see that as different kinds of variables that are available and that have to be dealt with and that have to be calculated statistically, analyzed statistically. But before we go into all these details, we need to understand how we actually record the data, and this must then be done, and the data must be entered in a spreadsheet, and normally that is then used the Excel program. If you enter data into a spreadsheet, you must always ask the questions, what do you want to answer? And then we need to apply relevant statistical tests, do the statistical calculations, and then actually start playing with the data. I always call it playing with the data because one must really get the fingers and the hands on this data to get the best results out of it. In the end, the data must be interpreted with relevant calculations. To create a spreadsheet, we need to follow certain rules. The first row, that is just the description of the data, that is the name, how this data, the name of the data, what is sperm count, motility, A, motility, B, total motility, or oxidation reduction potential, whatever. And a row represents a whole set of data that were taken. And columns like this then contain only one parameter that was taken. It must not be mixed up, otherwise all the calculations will be wrong. And each column must then have its unique name, which actually describes the very parameter that you are taking. And then, except for the first row, use numerical or categorical entries. With numerical, with the numbers, or for sperm count 20.2 million, whatever, or pregnant, yes, no, and entries like that. And this is then how the Excel spreadsheet looks like, but this is a real example that I actually received from students. And don't worry about this German. Here the big mistake is that here's a sperm concentration in one column with head defects. Eosine test in one column with elongations. And yeah, here these rows are, they are empty. So that's not to be used. But the main thing here, the different variables are mixed up. The second example that I have here is that the description of the variables, PN stage, score fragmentation, embryos, and so on, but this is not in row number 1. The rest seems okay, but in any case, you must actually check all your variables and your spreadsheet before you enter into any analysis. This slide now shows how it should be done. We have here in the first row the name of a variable, male age, older than 37 years, yes or no, BMI, and so on. And that goes right through. So here we have numbers, numerical, and with age older than 37, or younger than 37, that is categorical. It's a yes or no. Your BMI, overweight, yes or no. This can be analyzed. But further, we need to understand the collection criteria. These data must be accurate. And it must be unambiguous, because inaccurate and ambiguous data collection will then lead to false results. The whole spreadsheet must be consistent and it must be contextualized. And of course, if you have too little data available, then you're extremely limited with your analysis and your study will be less worth as if would be then comprehensive. So inconsistent and incomprehensive data collection leads to misinterpretation and incomplete interpretation of the data. Coming to the calculations now, these variables and parameters that I have here highlighted in red, like sample size, arithmetic mean, median, standard deviation, standard error of the mean, coefficient of skewness and kurtosis, and the normal distribution. These are the very first analyses that have to be done and that we have to understand what does it mean. So there are some important terms for summary statistics. We have the sample size, which is simply the number of cases of numerical entries of a variable that fulfills the selection criteria, which is called as n. Then the arithmetic mean, or commonly just referred to as mean, that is calculated as the sum of all observations divided by the number of observations. Then we have the median, which is defined as a middle value of a set of numbers, and it actually represents the 50th percentile of a set number. And this can then be either normal, represent a normal distribution, and there I'm actually referring to one other important aspect that I want to talk about later on, the normal distribution. The median is normal when the median is equal to the arithmetic mean. On the other hand, the median is not sensitive to extreme values or outliers, such as the arithmetic mean here. Going further into these important terms of summary statistics with standard deviation, which is just a measure of how dispersed this data is in relation to the mean, to the arithmetic mean. And it will then normally actually refer to as standard mean plus minus standard deviation, or mean plus minus standard error of the mean. And the standard error of the mean, excuse me, is simply a calculation by the division of a standard deviation here by the square root of the sample size. So SEM is equals the standard deviation divided by the square root of the sample size. And then we see, for specifically important for the median, the confidence interval, which is defined as a mean of an estimate plus minus variation of that estimate. So we see here lower limits and upper limits. And this should statistically be described as a 95% confidence interval. It is the mean plus minus 1.96 times of the standard deviation. And there we come to the important aspect, which is actually required for any additional and first statistical calculation, the distribution of the variables. That is a question about whether or not these data are normally distributed or not normally distributed. A normal distribution is normally following a bell-shaped distribution, a bell-shaped curve. On the other hand, often we see that the data is skewed to the left, and it looks like this. So we can see this, for instance, with age for a certain patient group, or skewed to the right when it looks like this. So it should follow this normal distribution. It should be symmetrical. On the other hand, we can also have a not normal distribution if that whole curve is flattened. Like here on the left-hand side, it's so-called platy-curtic distribution. It's flattened, which is also not a normal distribution. On the other hand, the opposite would be if it is heightened here in the center, it's also not normally distributed. So all these, this is a normal distribution, and this has serious consequences for all following statistical calculations. Looking at the mean and the median, the mean and the median are basically equal if there is normal distribution. You can see this here, and here on a real example, it's 59.6, is relatively close to 63.2. On the other hand, if the median is deviating from the mean, so if there's a huge difference, then we are talking about the sample is not normally distributed. And this is what we can see here. The arithmetic mean is 27.4, whereas the median is 21.4. So this is then not normally distributed as compared to the upper example here where it's the normal distribution. And like I said, the distribution of data that has consequences. If the data are normally distributed, then you can express your values as mean plus minus standard deviation. It can also be calculated for normal correlations like Pearson correlation coefficient, and parametric tests can be done, the t-tests and ANOVA. On the other hand, if the data is not normally distributed, then data have to be expressed with a median, and the range. And correlations have to be calculated with rank correlations. On the other hand, for comparisons, we need to use non-parametric tests like Mann-Whitney and Wilcoxon. So summarizing this, for normal distribution, the normal correlation coefficient, like Pearson correlation coefficient, can be calculated. If the data is not normally distributed, this should not be the case, then you have to use Spearman's rho, or if it is very much not normally distributed or very small sample size, then one can even use Kendall's tau calculation. But what kind of tests should be used for normal distribution? The most commonly used test is the Shapiro-Wilk test, which is more appropriate for small sample sizes, smaller than 50, although it can also handle larger sample sizes between 3 and 5,000. Other commonly used tests for normal distribution is the Kolmogorov-Smirnov test, but this test has less power than the Shapiro-Wilk test. Another test here, the D'Agostino-Pearson test, that is putting more emphasis on for the calculation on the skewness and kurtosis. So how do we then continue with our approach for statistical calculation? It depends on the sample. We have a control in the test. We do our summary statistics, and then the first thing is normal distribution and test for outliers. If the the data is normally distributed, then parametric tests for comparisons here, when there's paired t-tests, or if we have not normally distributed data, then there's Wilcoxon test. If we have different samples, then one sample is used as a control, the other as a test. Again, same story. Summary statistics, test for normal distribution, test for outliers. If normally distributed, then independent t-test. If not normally distributed, then non-parametric test as Mann-Whitney test. For correlations or associations, we have one sample with different variables and parameters to be measured. We want to find out, is there a association, a relationship between these different parameters? Again, same story, summary statistics, summary statistics, normal distribution, and if normally distributed, Pearson correlation. If not normally distributed, Spearman rank correlation, or when, finally, if you have data where you want to find out if there is a relative risk and if it is categorical data, for instance, if patient pregnant versus non-pregnant and varicocele, not varicocele, then we can calculate odds ratios and relative risks, where the odds ratio is defined as a measure of association between an exposure and an outcome. On the other hand, the relative risk, that is rather describing a probability of an event occurring in the exposed group versus the probability of the event occurring in a non-exposed group. And that will then be here, for instance, leukocytospermia, yes or no, in patients of high oxidation reduction potential versus low oxidation reduction potential. Here, where the exposed group would then be probably high ORP. And in this case, the relative risk is, as well as the odds ratio, there is no significant association. And with this, I would like to thank you very much for your attention. Thank you.
Dear colleagues, ladies and gentlemen, good morning and good afternoon, wherever you are. My presentation today is about comparing means between groups. Our agenda today will include discussing different types of data, descriptive statistics. We shall go through the null and the alternative hypothesis, data distribution, exploration, inferential statistics and comparison between groups, correlation analysis and univariate analysis. So in terms of data types, we have several types of data, either in programming field or in statistics field. Our presentation today is regarding the statistics, so we will be concerned about the statistics. The first type of data is a continuous data. So continuous data may be interval or ratio. The interval data is a numerical variable where the difference between values is meaningful, but the ratio is not. For example, temperature in Celsius or Fahrenheit, there is no true zero. A ratio data where both the difference and the ratio between the values are meaningful. For example, the height in inches, weight in kilograms, salaries. You do have a true zero. So you could say this subject has a true zero, is unemployed. So we still have a true zero here. The other type is discrete data. For example, number of children in a family. So these numbers are non-dividable, so it cannot be broken into smaller units. Categorical data, on the other hand, can take a limited and fixed number of distinct categories or levels. For example, gender, male or female, marital status, married or happy, and so on. Ordinal data is a categorical variable with inherent nature or inherent in natural order or rank. For instance, you can express hypertension as severe, moderate, and mild. You can still have categories. So it does have a meaning and rank. A binary, on the other hand, is two variables only, or two values, whether yes, no, true, false, pass, fail, and so on. Nominal data, on the other hand, does not have any kinds of orders, categories that have no inherent orders or rank. For example, eye color or a vehicle type. So there is no specific rank for that. It's always nominal here. So this is very important table. If you can see here, the ratio data is the king of numerical variable or continuous variables. So can be categorized, can be ordered or ranked, have equal spacing. It has a true zero. You can get the mean, medians, standard deviation. You can multiply and divide, add or subtract. And you can calculate arithmetic means as well. Interval data, on the other hand, it's the same as ratio data, but as we said before, it does not have a true zero. For example, is a temperature. You still have a temperature below zero. And you cannot multiply or divide. Ordinal data have inherent rank or order, but you can still get the mood, which is the most frequently observation in your sample. Nominal data, the only thing that you can do is get the mood. Okay, now let's move to the quantitative analysis. Why we do that? It could differentiate between groups. Like you can compare serum testosterone levels between men with and without clinical varicocele. or assess a relationship between variables, serum FSH, for example, and sperm count. Test hypothesis scientifically, efficacy of, for example, efficacy of a certain vaccine. So studying population is too labor intensive, time consuming, expensive, and maybe impossible. So instead, we need to get a sample. The sample basically descriptive statistics basically describe the sample, whereas inferential statistics aims to make a prediction about the population. And we will explore that in a moment. Let's say we have a hypothesis, or we assume that men are earning more than women in the United States. Your target is either to reject or retain this hypothesis. And since we have more than 160 million people working in the States, so studying them is maybe impossible. So instead, we need to have a sample, and the first part is to estimate a sample size. Then we must have a tool that measures that. So we will design, validate, circulate a survey. Then we collect the data and analyze it with the hope that this data, by using these sampling characteristics, to test the hypothesis about the population. So we have two hypotheses are formulated, which propound the opposite. The first one is the null hypothesis. There is no difference between the groups. For example, in our example, in the United States, the annual income of men and women is the same. On the other hand, the alternative hypothesis, there is a difference between groups. For example, in our example, in the United States, the annual income of men and women differs. So what's the probability? The probability of the observed results plus the extreme results, assuming that the null hypothesis is true. This is basically what we do. We set a significant level before examination. Let's say we set this set level at 0.05. If the p-value is less than 0.05, this is significant, and we reject the null hypothesis. That is to say, there is a significant difference in the income between men and women. On the other hand, if the p-value is above 0.05, that is not significant, and then we retain the null hypothesis. In other words, we don't have a difference in the income between men and women. So, however, because statistics comes from samples comes from the population, we still have a chance of error. The first type of error, when the alternative hypothesis is confirmed, while in fact there is no difference in reality. In this case, the null hypothesis is valid. And this is called type 1 error or alpha error. The opposite is true when the null hypothesis is confirmed, while there is a difference in reality. In this case, the alternative hypothesis is valid, and this is a best example of type 2 error or beta error. Now, what comes to data distribution? We have two ways to identify or explore data regarding the distribution, whether it is analytical or graphical. Analytical, we use a test like Shapiro-Wilk test or Kolmogorov-Seminar test, KS test, to test the normality of distribution of data. Or we could use a graph. A visual assessment complements a statistical test. For example, a histogram plot or QQ plot. And we will explore that immediately. So in this slide, we can see on the left-hand side a bell-shaped curve. Under the bell-shaped curve, we have our observations. In the middle, we have the mean. If you took one standard deviation above and below the mean, that should cover 68% of your observations. If you took two standard deviation above and below that mean, you would cover 95% of your observation. This is typically what you see when the data is normally distributed. On the right-hand side, you can see the QQ plot where the observation here is pretty close to the line. So when you see this figure, this is a typical picture of a normal data distribution. However, in many cases, the data is abnormally distributed. For example, let's see this histogram. This histogram from a true data that is retrieved from the GAF Andrology of Practice survey that we have circulated recently. And it shows you the number of articles published. If you see here, the bell-shaped curve here is asymmetrical. It's unlike that one that we saw previously. It's asymmetrical. And you can see the QQ plot, it forms like an arc with many observations away from the line. And this is typically what we see when the data is abnormally distributed. A stem and leaf, it's like a tree. When you have a stem and leaf, this is also another plot to explore the data. Whether have a symmetric data on the left-hand side, right skewed or left skewed. In our number of articles published, we have a typical picture of right skewed data. We can also explore data in terms of means and medians and so on. Look for this slide, for example. The mean is 37, the median is 14. Typically, in a normally distributed data, the mean is pretty close to the median. Also, when it comes to standard deviation, in a normally distributed data, the standard deviation should be less than the mean. In this case, it's even higher. In a normal distributed data as well, the range should be narrower than that. We have a very wide range of 0 to 500. Then we look to the skewness, where it's 3.56. Typically, in a normally distributed data, the skewness should range between -2 to +2. Outside this range, the data is abnormally distributed. What about kurtosis? Kurtosis also is another parameter for normality distribution. It should range between -7 to +7. If it is outside this range, the data is abnormally distributed. And look to this graph, also for the number of articles published. It shows you the means, the standard deviations, plus you can see here the outliers. These are the observations that outside the mean. They are the outliers. And these numbers are not typically the observation, but it's typically the case or record number. If you can see here, if you go back to record 55 or 25, you would see that this is 500. That's important because sometimes the outlier could be due to error in data entry. It is not something by nature. So you have to explore your data, clean it up, and then you proceed with your analysis. However, when you're using skewness and kurtosis, it's very, very sensitive to sample size. When the sample size is below 300, we usually divide the skewness and kurtosis by the standard error of mean to obtain the z-value. The z-value should range, if the sample size is below 50, should range between -1.96 to +1.96. If the sample size between 50 to 300, the z-value should be between -3.29 to +3.29. However, with sample size above 300, we don't use the standard error, we don't use the z-value, we take the absolute skewness and kurtosis. And this example, as we illustrated before, we have the skewness and kurtosis 3.5 to 16.89 respectively. Now, let's move to the analytical test. Okay, so sometimes you need to do the test just to confirm. For example, in this case, we did a Kolmogorov-Semenov test and Shapiro-Webb test on the data distribution for the numbers of articles published. Look to the p-value. Here it's 0.0001, so it's very significant, highly significant. If the p-value is less than 0.05, in this case, we reject the null hypothesis, and the data is not normally distributed. But if the p-value is above 0.05, is not, so it's greater than 0.05, we accept the null hypothesis. And in this case, the data is normally distributed. Okay. What about comparing between two independent groups? The two independent groups mean the groups are not related to each other. Two different separate groups from two different populations. Now, if the data is normally distributed, we ask a question, is there a difference in mean? Then in this case, we are testing difference in means. To qualify for this test, the two groups must be independent, the data is continuous, data must be normally distributed, and variances within the groups should be similar. When you fulfill this criteria, you can confidently use the independent t-test. So what happens if the data is abnormally distributed? We use in this case a Mann-Whitney test. A Mann-Whitney test asks if there a difference in the rank sum. So in this case, you cannot use the independent t-test. You must use the Mann-Whitney. Why? Because the data is abnormally distributed. Okay. How we do that? We rank our observation. So the smallest first observation is ranked 1, followed by the second smallest 2, and then third, fourth, until we rank all the cases. Then we add up ranks, and then we compare the U or the total sum ranks. To qualify for this test, the two groups, again, must be independent. The data is continuous or at least ordinal. Data does not have to be normally distributed. This test is immune to data distribution. Okay, what about before and after design? This is called the dependency because you basically test a group before and after. So again, in this case, if the data is normally distributed, we used a paired t-test and sometimes called dependent t-test. If the data is abnormally distributed, we use the Wilcoxon signed rank test. So what we do? Again, we have a group before. Then we do intervention. This intervention could be surgical, like varicocele repair. Could be medical, a new medication or drug. Could be behavioral therapy, or change even a lifestyle. Any intervention could happen. Then we have a time. You test again. This could be after seconds, minutes, or hours, months, years, whatever. So this is basically a test before and after. Based on the data distribution, we use a pair t-test or Wilcoxon signed rank test. But we cannot use the other test that is used in independent comparison. Now, what about if we have 3 or more groups? Okay, again, the same thing. If the data is normally distributed, we use the ANOVA. It's called analysis of variance. This basically tests the difference in the mean between in the mean values between the groups. But if the data is abnormally distributed, we use the Kroskal-Wallis test or Wallis test, and we ask the question: is there a difference in the rank totals? How we can do that? The same as we did in Mann-Whitney. So we rank the cases. We cannot use the mean here. Why? Because the data is abnormally distributed. We rank the cases. So the smallest first observation is ranked 1, followed by the second smallest observation, then the third smallest observation, until we rank all cases. Then we add up ranks to get the total rank, the rank totals. And then we compare the rank totals. Again, the data does not have to be normally distributed. This is immune to data distribution. Now, let's apply what we have learned to a true example. You say you want to compare sperm concentration and serum FSH levels, and you have 2 groups of patients. The first group is 25 infertile men without varicocele. The second group is 20 infertile men with subclinical varicocele. And you need to test for normative distribution. If you look to the table here, you would find in both cases, like the mean 22 is pretty close to the median. The same for serum FSH 4.1 is close to 3.9. The standard deviation is smaller than the mean in both cases. You look to the confidence interval, which says that 95 observations lies within this confidence. You look at the skewness and kurtosis, you cannot swear about that. You cannot you are not pretty sure if this is normally distributed or abnormally distributed, then you go to the QQ plot. Again, if you look to the sperm concentration, okay, that's pretty nice now. The QQ plot shows here the observation is closer to the line as compared to the serum FSH. It's not that close. So again, this is more or less normally distributed for sperm concentration, but not for a serum FSH. Then we have to do a test, okay, just to confirm. Okay, we do in this case a Kolmogorov-Siemenov test. And the p-value here is insignificant for the sperm concentration, but it is significant for the serum FSH. In this case, you can say with confidence that in sperm concentration, the data is normally distributed, while in FSH, the data is abnormally distributed. So let us advance that, okay. Which test could be used? Like this table shows sperm concentration and serum FSH, and you want to compare which of the respective tests are appropriate for comparing between the two groups. Give you like a few seconds to think of it. Okay, let's tackle it one by one. So ANOVA is a parametric test that tests the difference between 3 or more groups. Do we have 3 or more groups here? No, we have only 2 groups. So ANOVA test is unsuitable. The independent test, on the other hand, compare between 2 groups. The groups must be independent and must be normally distributed. And we know that sperm concentration is normally distributed. So independent test is correct, but you cannot use it for serum FSH. Why? Because serum FSH is abnormally distributed. Anderson-Darling test is a test for testing the normality distribution. It is not used to compare between means. So it's not applicable. Kruskal-Wallis test here is the alternative, is a non-parametric alternative to ANOVA. So again, 3 or more groups, we don't have, the condition is not fulfilled here, so we cannot use it. Mann-Whitney, on the other hand, is a non-parametric test that compares between 2 independent groups. In this case, the serum FSH is abnormally distributed, so we can use a non-parametric test. So Mann-Whitney test is a suitable one. A Perty test is dependent, so it compares before and after, and this is not the case here. We are comparing 2 independent groups, so Perty test is not suitable. So as you can see, it's very easy. You just have to know the rules. You have to follow the normal sequence, and then you get your conclusion with pretty confidence. Now, to sum up, if you have two groups, yes. Data is normally distributed, yes. We use the independent unity test. If the data is abnormally distributed, use the Mann-Whitney. If you have 3 or more groups and the data is normally distributed, use the analysis of variance. But this one more step. If the analysis of variance is significant and you have 3 or more groups, we are interested to know which group is causing this significant. In this case, there is another step called a post hoc test. And the commonest one done is the LSD, or least significant differences, to identify which group is causing the significance. And if the p-value is insignificant, we don't proceed with the LSD because all the results will be insignificant for sure. Now, the same thing for abnormal distributed data, we use Kruskal-Wallis. Again, if the p-value is significant, we use a Duns test to show which group is causing this significance, and if it is insignificant, we stop. Okay, now a correlation. Correlation is used to understand a relationship between variables, usually dependent and independent variable. Let's say we want to see the relationship between rains, a number of rainy days, and the numbers of umbrella salts. So we plot this relationship on this curve. The independent group, which is rains, will be the x-axis. The dependent group will be in the y-axis, which is number of umbrella salts. And we drew the relationship, the correlation, or the scatter plot. You can see the observation here. When the observation here is pretty close to the regression line, then the data has a strong relationship, strong coefficient. If the data is scattered away or not pretty close to the regression line, then the relationship, we conclude that the relationship is much weaker. Okay, though this table is very important, this slide is very important as it shows the relationship and the correlation span. So, first of all, correlation is not a causation. Causation occurs when something happens that leads directly to the other event. That is supported by theory, supported by and has a temporal relationship. Correlation is not a causation. This is number one. When you have a zero relationship, that means there is no correlation. The scatter plot is totally irrelevant. Zero relationship. -1, because the coefficient would range from -1 to +1. -1, you have got the strongest negative correlation. +1, you have the strongest positive correlation. In this figure, we can show the correlation coefficient. For example, if you go to the upper graph here, you can see R equal 0.7. This means a strong positive correlation. And -0.4, that means it's a moderate negative correlation, and so on. Let's have another example, which is very simple. Let's say that we want to test the relationship between the acceleration of a vehicle and the dependent variables. So the independent variable with the car speed or is better acceleration of the vehicle. What are the factors that affect that? So it could be the engine power, could be the vehicle weight, the aerodynamics, the slope of the road, and the transmission. Could be other factors. So these are multivariate, okay. Now, if you take one of them like engine power, this is called simple regression analysis. You take only one variable, that's the engine power. It's simple linear regression, and this is the curve, y, which is the independent variable, the value of it, equal mx plus b, where the m is the slope, the x is the dependent variable, which is here is the engine power, and b is the y-intercept. If you do your regression test, you can get the slope, and you can get also the y-intercept, which is the b, and it's very easy here to know or to predict the y. But since we are taking one variable only, which is the engine power, it's called simple linear regression. When you take all the variables together, it's called multiple linear regressions. If your independent variable is a categorical, this is called logistic regression. I think Professor Ahmad Haraz will present you the regression analysis in detail. I hope you enjoy his presentation. Thank you so much.
Dear Chef Management, thank you so much for giving me this opportunity to present comparing proportions between groups. First, this is a screenshot of the SPSS program, my favorite program to perform statistical analysis. As we can see, each row represents a case, and each column represents a variable. The first variable is the age, which is a continuous variable or a scale variable because it can be measured on a scale, which is years. The sixth is a categorical variable or a nominal variable because it is composed of groups. In this case, it's composed of male and female, two groups. The weight and the height are both continuous or scale variables. The nutritional status, again, is a categorical variable because it's composed of two groups, good nutrition or malnutrition. Tumor grade is also composed of multiple groups from 1 to 4, but because these groups are ordered, we call it ordinal variable. Treatment success is a categorical variable which is composed of two groups, success versus failure, and in the same time, this is the primary outcome of the study, or as we call it, the dependent variable, because it depends on the previous variables, which are the independent variables. In this part of the lecture, we will discuss the categorical or the nominal variables, for example, the sex and the treatment success. The first question is how we describe the categorical variables. We describe categorical variables in terms of frequency and the percent in each category. For example, male constitutes 245 patients, and they are 61.3% of the whole study population. Females are 155, which is equivalent to 38.8% of the whole population. Another example is the treatment success. The treatment success, patients who are succeeded are 301, and this is approximately 3/4 of the study population. And the failure, patients who failed, constitutes 24.8%. So when we describe categorical variables, we describe the frequencies and the percent in each category of these categorical variables. The next part is how to study the association between two categorical or nominal variables. For example, how many males who succeeded and how many males who failed. How many females who succeeded and how many females who failed. We construct a table, which is 2x2 table, according to the number of the categories. We usually construct the table with the columns represent the primary outcome or the dependent variable, while the rows usually are the groups of the independent variable or the predictor of the outcome. In this situation here, we can see that 20.4% of males failed compared to 31.6% of females. We are now comparing proportions between groups. So it is obvious that females are more likely to fail when compared to males. This is how we construct and interpret a table of categorical variables. Now the question is this difference statistically significant or not? From the previous study, from the previous table, we saw that females are more likely to fail the treatment when compared to males. So what is the appropriate test to drive the p-value to know whether there is a statistically significant influence of the sex over the treatment or not? In this situation, we usually depend on the chi-square test. This is the output from the SPSS, and we are particularly interested in this number, which is 0.01, which is less than 0.05. So we can say that females are more likely to fail the treatment when compared to males, and this is statistically significant because the p-value of the chi-square test is statistically significant and it is less than 0.05. Let's go to another example. We are now testing the association between the nutritional status and the treatment success. As with the previous example, we can see that 0 patients with malnutrition has failed the treatment, constituting 0% of the study population, in comparison to 99 patients constituting 25.2% of patients with good nutrition. It appears to me that patients with good nutrition, 25.2% has failed have failed the treatment compared to 0% from those with malnutrition. This means that good nutrition appears to fail the treatment. Okay, so the next question is this a statistically significant difference or not? In this situation, we can't use now the chi-square test because the chi-square test has an important rule that any cell of these should contain number more than 5. And if it contains number less than 5, we will use the Fisher's exact test. So all what you need to know that we use the Fisher's exact test when the cell, one of the cells of the table contain count less than 5. We can see here, this is the table which shows the association between nutrition and the treatment success. And here is the result of the chi-square test. As we can see, there is an alarm that there is one cell has expected count less than 5. So we can't use the chi-square test. We will use only the Fisher's exact test. So the whole message from this is that when we test the association between two categorical variables, we will use the chi-square test. And the p-value is derived from the chi-square test. But if any one of the cells contain number less than 5, so in other words, there are limited number of one of the categories, we have to use the Fisher's exact test rather than the chi-square test. You don't need to know how we do that. You don't need to know the technical aspect of this or why, but all what you need to know is that the p-value is derived for categorical variables by the chi-square test or Fisher's exact test as indicated by the number of patients in each category. To consolidate this, the p-value of the Fisher's exact test is 0.2. So the results that we have obtained from here is not statistically significant. It can't be generalized. And this is actually explains why people or patients with good nutrition fail the treatment rather than those with malnutrition. So by this p-value, we can say that these results have been occurred by chance and they are not statistically significant. We knew that females were more likely to develop treatment failure when compared to males. The question is, by how many times females are more likely to develop the treatment failure in comparison to males? Actually, the answer of this question, it depends on the type of the study. Because in retrospective studies, we already know the outcome. We already know the patients who failed or succeeded the treatment, and we will look back in time to see how many females or in comparison to males, which of them is a predictor for this outcome. Think with me if we are doing a prospective study. The condition is different because in a prospective study, we included males and females in the study, and we will look forward in time to see who will succeed and who will fail the treatment. So the question should be tailored according to the type of the study. Let's start with retrospective studies. In retrospective studies, we already know the treatment outcome, and we will look backward in time to see the predictors. So what we will calculate the risk of exposure to the predictor that achieved this outcome that we already know. For example, in this situation, consider this a retrospective study. So we will use the odds ratio. to calculate the risk and to answer the question by how many times patients who failed the treatment were females in comparison to males, because we will calculate the odds of the risk factor, because this is a retrospective study. Now, we will calculate the odds of females in comparison to males who failed the treatment. So the odds of being a female in comparison to male equal to 49 divided by 50. And the odds of being a female in comparison to male who succeeded the treatment equals to 106 divided by 195. By dividing both ratios, we will have the odds ratio of 1.8. So what 1.8 represent? 1.8 represent the comparison between females and males with the likelihood of failure, the treatment success. So in patients with treatment failure, the likelihood of being a female is 1.8 times in comparison to the odds of being a male. I hope this is well understood, because we are looking back in time and we are calculating the odds of the predictor or the risk factor. Let's go now for the next condition. In prospective studies, we know the risk factor, we know the exposure, we know being male or female, and we will look forward in time to see which category will succeed or will fail the treatment. So we will now calculate the risk of the treatment outcome. So the risk here, the risk of female to fail the treatment, in this condition, we will calculate the risk of female to the total number, not female to male. And this is what we call the risk. This is the risk. In the last slide, we calculated the odds. The odds, we will divide the number of females by the number of males. The risks, we will divide the number of females and the total number of failure. So it will 0.49. And we will calculate the risk of females who succeeded, which is 1.6 divided by the total number. And we will calculate the risk ratio. The risk ratio is dividing the two ratios and will give us 1.4. So the interpretation now is females are 1.4 times more likely to develop treatment failure in comparison with males. It's all about calculations. Odds ratio, the odds are calculated by dividing the number of females to the number of males. The risk is calculated by dividing the number of females and the total number of failure. The number of females divided by the total number of success. Why is this difference? These are all mathematical issues that we are not concerned about. We are not mathematicians. We are clinicians, and we just apply the rules. So in retrospective studies, we use the odds ratio to calculate the risk. And this risk is the risk of exposure to the predictor, the risk of exposure to a risk factor. In prospective studies, we will use the risk ratio, which calculates the risk of the outcome, because we already know the exposure and we will wait the outcome to happen, because this is the definition of prospective studies. So, in summary of the odds ratio and the risk ratio. Odds ratio is used for retrospective studies. It estimates the odds of having a risk factor in a well-known outcome, because this is the definition of retrospective studies. We know the outcome and we will calculate the odds of having a risk factor. On the other hand, risk ratio is for prospective studies. It estimates the risk of developing the outcome if you have the risk factor. So by default, odds ratio or risk ratios are ratios. So if the ratio equal 1, this means that both comparisons are equal because it equal 1. So in summary, if the odds ratio or risk ratio equal 1, this means that there is no increase in the risk. Likewise, if the odds ratio or the risk ratio is more than 1, there is an increase in the risk. And the odds ratio or risk ratio is less than 1, this means that there is a decrease in the risk. Last part of my lecture is about logistic regression analysis. Suppose that we have multiple predictors for the outcome. The multiple predictors, as in our example, as I showed you before, the age, the sex, the nutritional status, the tumor grade, and all of these are both possible predictors to the outcome, which is the treatment success or failure. In logistic regression, the outcome must be a binary variable. Binary variable is a categorical variable or a nominal variable that has two categories, only two categories. So we use this logistic regression for binary outcome variables, a variable that have only two categories, success versus failure, life versus death, yes versus no. It should be two categories. And by this regression method, we will calculate or we will determine the independent predictors that are associated with the outcome. This is an example of a logistic regression analysis. And we entered all possible predictors together to calculate or to predict the outcome. The analysis will calculate for us the odds ratio for every category, and by default we need a reference. So females, for example, have an odds ratio of 1.5 in comparison to male. In tumor grade, for example, grade 1 has a reference, grade is the reference, grade 1 is the reference, grade 2 is 2.9, more likely to develop the outcome compared to grade 1. Grade 3 is 7.2, more likely to develop the outcome in comparison to grade 1, which is the reference. And it will yield for us the p-value, and according to the p-value, we can know which variables of these are independent predictors of the outcome. I hope that this introductory lecture sheds a light on the categorical and the nominal variables and estimation of the risk. And again, thank you so much for listening, and thank you so much, Zijab, for this opportunity, and have a nice day for everyone. Thank you so much.
Hello, everyone. Thank you very much. I come back again here to summarize and to introduce you to the Global Andrology Forum. First of all, I want to thank our excellent speakers, starting with Dr. Nicolas Garrido. Secondly, Professor Ralph Henkel, who unfortunately could not be here, but he provided us the presentation. Then came Professor Wael Zodi, who's currently in Canada. Dr. Garrido is in Spain. Dr. Henkel is in UK near London. And lastly, you heard from Dr. Ahmed Haraz, who I believe either is in Kuwait or in Egypt. He was vacationing earlier, but he works in both places, but mainly in Kuwait. So excellent presentation. I could not have found another speaker. I think they are all members of our Global Andrology Forum, and I'm going to introduce you briefly as to what this organization is. And after my 15-minute presentation, I will have Dr. Garrido summarize and finalize and end the presentation after mine. So this is the last part of it. I just wanted to tell you that what you have heard from all the speakers today should really sensitize you that statistics may not appear very sexy subject or topic. And I know many people are scared of the statistics. But nevertheless, of course, it is a crucial thing for the researchers. This is not really an issue of anything to discuss. But for clinicians who are primarily responsible for taking care of the patients, are not really immune from statistics. This is something they must learn, because for today's clinicians, it is really not just taking care of the patients and treating them and managing them, but knowing the statistics really is a crucial thing, because it really allows them to make informed decisions about patient care. They can better understand the risk and benefit of different treatment options, and they can make more accurate prediction about the likely outcomes of different courses of treatment. This is one of many different reasons why statistics is really crucial. And now I would like to really tell you about the Global Andrology Forum. I have requested Ms. Liliana to project my presentation because my internet speed is not really very good today for some reasons. So she will move the slides. So Liliana, please keep on moving. Next. So please click. I just wanted to introduce you what is andrology, because of course this program is under the ambit of Global Andrology Forum, and many of you who are attending today are not members of the Global Andrology Forum. So it is really incumbent upon me to explain andrology is a specialty of medicine which focuses on the study, diagnosis, and treatment of conditions related to male reproductive system. Next. It includes various aspects of male reproductive health, including the structure and function of male reproductive organs, and as well as disorders such as erectile dysfunction. Next. And in addition to diagnosing and treating medical conditions, andrologists may also counsel and guide on reproductive and sexual health. Last, next. And it is one of the most important field because it plays an important role in addressing the male reproductive health issues, promoting fertility, and ensuring overall well-being for men. Next slide. So what is Global Andrology Forum? And this is something that many of you who are not members may be thinking, what is this organization? Well, it started about 2 years ago as an international online group collaborating for andrological research, was formalized in December of 2021. As of today, maybe this number is not highly accurate, but at least 637 participants from 81 countries are part of this group. It includes andrologists, urologists, uroandrologists, gynecologists, embryologists, even psychologists, reproductive endocrinologists, researchers, medical residents, students, pretty much all kind of groups or individuals who are interested in the field of andrology. Next slide. Our mission is to conduct the highest quality research, including systematic review, meta-analysis on controversial topics in male infertility, new cytometric studies in the field, and to write cutting-edge articles on the future of male infertility and sexual medicine. Next. Our vision is to create a global collaboration of clinicians and researchers, bring everyone together to promote scientific excellence in the field of andrology. Why? Because the field of andrology really lacks high quality, high evidence studies, which is really impacting on the treatment of men with problems of male infertility and erectile dysfunction. And this is the really main reason that we want to bring up this field by really going to the foundation of creating high quality, high evidence research studies which can be published in high impact journals. Next slide. Next. As of now, as you see, our membership just within 1 year, I think has grown almost like 40% already, and it continues to grow from every part of the world. Next slide. This is a breakdown of the membership, as you can see, from many different parts of the world, and we welcome many of you who are not members to please apply for the membership. Next slide. Our main members are andrologists and urologists, but we have, as you can see, people who are embryologists, IVF specialists, clinicians, endocrinologists, gynecologists, etc. Next slide. A lot of researchers. Our main objective is to conduct high quality research, training in research methodology, knowledge dissemination. Next. We do this by conducting high quality online research with systematic review and meta-analysis. We conduct a high level global survey on various controversial topics which are not suitable for systematic review and meta-analysis. And we also conduct we write and publish opinions and perspective and editorials. Next slide. We use meta-analysis and systematic review because these are the highest level of highest quality of evidence, and it strengthens the quality of science in our field. Next slide. We conduct global survey. It provides unique perspective on the topics. For example, we have done on non-obstructive azoospermia. We've done on sperm DNA fragmentation. Currently, we are working on regenerative medicine. So there are a large number of studies that are going on in the form of global survey using all the physicians and clinicians and researchers who are already members, as well as people all around the world who we invite to participate in these online surveys. Next slide. We write opinion papers, engage senior members. There are a number of studies that are going on, which I will describe in the next slide, please. A lot of studies, as we discussed, we started projects on male sexual dysfunction this year, and there are a large number of both meta-analysis, global surveys, and articles are being written. Next slide. Next. The studies that need global inputs, large multi-institutional studies, proposals invited from GAF members. And this is the way that many of the studies are being done, including hundreds of researchers and clinicians working together and benefiting from authorship in high quality journals. Next slide. We have collaboration and affiliation with large number of societies, and more collaboration is happening every day, and we will have a very large number in the next several months of many other societies who are working with us right now to sign up the agreements. Next slide. We have conducted a large number of webinars, and these are some of the examples of the ones that we conducted last year. And each one of them have been attended by very large number of candidates from all over the world. Next slide. And you can see each individual course or each webinar is attended. For example, this one, which was last year, was attended by over 1,700 participants from 81 countries. And we had a similar type of format where the participants were allowed to take a pre-test and later on a post-test. And those who scored more than 75% earned a certificate of training. And those who attended the program, get a certificate of attendance. Next slide. These are the benefits of attending the program. Next slide. You can see we have some statistics also for our colleagues, which shows the level of understanding before the webinar was conducted and after the webinar was conducted. And these results are strikingly showing an impact of knowledge acquisition as a result of the talks and lectures that were delivered by our faculty. We are going to do the same thing today for those who are taking the test, who have taken the test before, because we are going to open the website again for you to take the test to see how you improve your results after listening to the lectures from our speakers. Next slide. And you can see these results are statistically significant, highly significant, P.001. So this is just telling about the results pre and post of the webinar. And this is for one of the courses that was taken. Next slide. We have a lot of things that we accomplished in just 1 year. This is the tally from last year with over 19 articles, original articles, which were published in PubMed Index High Impact Journal. We conducted many webinars and presented many papers at international and national meetings. Next slide. These are some other accomplishments. We have workshop and masterclass at SIU, which is Society International Urology. We launched training in research methodology, launched 10 new systematic review and meta-analysis. So we are extremely busy with large number of projects that are going on. Next slide. And we have a goal of, or at least even now, we have over 25 articles which have been published or accepted in this year. And this is only half of the year. And more than 98 chapters are being written. And we have 3 more books and a special issue which have opened since in the last 2 weeks itself, that will increase the number of opportunities for writing to over 200 such articles. And we have a large number of projects which are opening up in sexual medicine. So we are extremely excited about our academic activities. Next slide. So this is the metrics that I want to present from today's. Next slide. It's just the registration data. Next. So you can see we have almost 595 people who have registered for today's program from 64 countries. So we are very proud that so many of you have decided to register and attend this very unique course, something that has not been seen to be done in any part of the world. In my knowledge, we have not seen such a course being offered at a global level. Next slide. And the course is completely free. And these are the registration by specialty. As you can see, people are from all different backgrounds. Next slide. So we have both male and female. You can see about 30% of our attendees today are female. Next slide. and about 40% of them are in private, 60 in public practice setting. Next slide. And the reason why they wanted to attend this is something that all of you have written by yourself, and this is the response from 595 of you who are have registered. Mainly, majority of them actually is the middle bar, as you can see, to improve my knowledge about medical statistics, but equally important are the reason to learn the best practices for statistical analysis in online research and to learn how to do scientific research. So all equally important reasons why you chose to attend. Next slide. Now we asked, are you a member of the Global Andrology Forum? And actually only 45 or 46% of you are members and 54%. So a huge number of you who are attending the program or who registered for the program are not a member, and we welcome you. Next slide. And we asked if you would like to become a member, and majority of you, 85% said yes. So we are very happy. Next slide. We will be delighted to welcome you among our organization, which is completely free and really focused. And you asked when we asked, would you like us to send you information about our organization? Majority of you, 90% of you said yes. So we are going to later on send you an email with the information, and if you would like to apply, you can apply. It's a very simple process. It takes maybe 15 minutes, and you walk through the process of reading about our policy procedures and what we offer, and essentially upload your CV, and we will get back to you after we have had a chance to screen your application. Next slide. Do you have any previous experience? Well, a large number of you said yes, while others didn't have any experience. So we have a fairly good mix of people who are attending. Next slide. I hope those, and this is our management. You can see this actually picture is not completely up to date because we have some other members who have joined as guest advisors, and which needs to be updated. But by and large, the program is administered with the help of the volunteering time that everyone contributes to run the program, set the policies, set the agenda, set the goals for what we are trying to do, set the research goals, supervise many different activities. But we also have a large number of research leaders who are conducting and guiding systematic review studies. There are 12 teams, and each team is being managed by different people. Oh, please go ahead. So now I wanted to just play a song about Global Andrology Forum, so you can listen, and then we'll come back. So this is a song that was being written by ChatGPT, and it was composed, actually was sung and composed by my son, Neil Agarwal, last year, and we played it. So I wanted to play it in every event so that you can learn a little bit about global andrology. It will take only a minute, and then we come back. Please go ahead.
This is a song about the Global Andrology Forum, empowering men's health, shaping the future together. Written by ChatGPT, performed by Neil Agarwal. Take 3. Men from all nations gather round with a common goal to be found, improving health and wellness for our fellow men's success. Global Andrology Forum, bringing hope and healing to the world. For every man in every land, together we take a stand. Experts from near and far share their knowledge without a bar, advancing science every day, making life better in every every way. Global and
It is stopped.
technology form, bringing hope and healing to the world. For every man in every land, together we take a stand. Let's work together side by side with compassion, love and pride. For the future, let us strive, make a difference, come alive. Global Andrology form, bringing hope and healing to the world. For every man in every land, together we take a stand. For every man, we'll find a cure. With knowledge, strength, and love secure. Global Andrology form. For every man, for everyone.
So this was a ChatGPT title song for Global Andrology. Next, just one or two more slides before I hand it over to.
This is a song about the Global Andrology Forum.
Yeah, this is a collage of people who are working. This is a small group of 637. So you can see they have all joined. We'll make history in andrology. If you want to join us in this global adventure, the time is now. Next. So you can become a member. It's very easy. Just go to our website, globalandrologyforum.com, and you can find it on the internet, and you can apply. There is a link to the application form, and the membership is free, the application is free, and there is never a fee of any kind for anything, whether it is a course, whether it's a training, whether it's a webinar. All of those activities, as well as your participation in various projects that we are offering, is completely free, and it will always remain free. So why not join? I think I would like you to at least visit our website and learn more. Next, I think this was the end, I believe. So this ends my presentation, and I want to thank my colleague, the speakers who have done a remarkable job by contributing their time and knowledge today with all of you. I want to invite Dr. Nicolas Garrido to conclude this program and take it over from now. Nicolas. You are muted right now.
Can you hear me now? Thank you so much. So first of all, thank you for letting me coordinate this webinar and also to conclude today's sessions. Just a few words to conclude today. First of all, I would like to thank Dr. Agarwal, Dr. Shah, all the management team, also Liliana Ramirez for her support on organizing all the work related with today's sessions. And of course, a big thank you to my colleagues, Dr. Sodi, Dr. Harras, and Dr. Henkel. It's a pleasure working with such amazing team in this webinar. So all questions have been responded during each session. So in summary, the aims for today, I think, have been widely achieved. We try to introduce everybody about the basic concepts on statistics, what are statistical analysis for, how to read the information, how to interpret data, how to make the less complex comparisons in order to gather rapid information from any data set you may have created during your research, because biostatistical techniques are just tools needed not only for those of you aiming to plan or do research involving data analysis or interpreting information gathered from a research project. It's also needed for correctly reading scientific literature, extracting the right messages, and adapting your clinical practice to the best knowledge available. Having a strong background in stats requires years of learning, and these were just introduction to the most needed topics that probably will be developed in subsequent sessions and webinars to come. So I hope you are interested in next activities, and on behalf of the organizing committee, the speakers, I would like to thank you all for your attendance and wish you a wonderful weekend. And just remember that statistics are numbers that tell stories, so you don't need to be afraid of that. Thank you so much for being here today.
Thank you very much, Nico. In conclusion, I just want to tell all the participants that a recording of today's program will be made available as soon as maybe even by tomorrow, because it needs to be reviewed and edited, and then it will be uploaded on our website, and a link will be shared by Ms. Liliana to all the people who have registered for this course. So please wait. But in the interim, Liliana is going to send you the link to start the post-test, which will be available to all of you. And for those who have done the pre-test, and if they do the post-test, and if they score more than 75% in terms of the correct answers, they will earn a prestigious certificate of training. All of those who are not doing both pre and post and score higher will still be eligible. They can take the test if they want. They will still get a certificate of attendance. So I just wanted to tell all of you, everybody wins here, nobody loses. And thank you very much, each and every one of you, as well as all the participants who came to attend this program. We thank you, and we look forward to further engagement in the future. Thank you very much. And this concludes our program on medical statistics today. Thank you and have a wonderful day. Bye-bye.